These are the answers to homework 1A. Here are the definitions I'd like you to know, and now let's go on to the questions. Number 1, calculate the molarity of sucrose in urn brew if a 500 milliliter bottle of urn brew contains 52 grams of sucrose. If you want to calculate molarity, molarity is defined as moles of solute per liter of solution. The solute's what's dissolved, that's the sucrose. The solution is the mixture of the two combined. They said you had a bottle of urn brew that's 500 milliliters, that's the volume of the solution. So we have to calculate how many moles of sucrose are in it. To calculate moles of a solute, you have to use its molar mass to convert the grams into moles. Molar mass of sucrose, 342.32 grams per mole. Because the 52 is a two significant figure number, the number of moles of sucrose you get will be two significant figures, 0.15. But when you're in the middle of a calculation, you don't want to actually round the number to two significant figures at this point, so we always keep at least one guard digit. The next digit in the calculator was a 2, so I'm going to write down 0.152 moles of sucrose, but I'm going to realize at the very end that really this is a two significant figure number. To calculate the molarity, you take the moles of the solute, you divide it by the solution's volume in liters, and 500 milliliters to three significant figures would be 0.500 liters. We're dividing a two significant figure number by a three significant figure number, so your answer is going to come out two significant figures, and we get 0.30 moles of sucrose per liter of solution, or 0.30 molar of sucrose for the molarity of the solution. Number 2, complete an initial, change, and final molarity table for each of the following reactions. We're going to assume these reactions go to completion. And in part A, we're given 3.0 molar of A, 3.0 molar of B, and we want to find out what's going to be in the container at the end of the reaction. You have to determine which of the two reactants, A or B, get completely reacted away. If A completely reacts away, that means all 3.0 molar of A would have to react in a 1:2 ratio with 6.0 molar of B. You don't have that amount of B, so therefore A is not the limiting reactant. B is the limiting reactant, so 3.0 molar of B will react away, and that's why I put a negative sign there. It will react with, in a 2:1 ratio, 1.5 molar of A, and because A and C are in a 1:1 ratio, you're going to form, so therefore a positive value, 1.5 molar of C. Adding up the columns, we'll have 1.5 molar of A left, no B left, and 1.5 molar of C created. For B, we're given 4.5 molar of D, 2.0 molar of E. We want to find the final molarities. If D is the limiting reactant, and D and E are reacting in a 3:1 ratio, 4.5 molar of D would react with 1.5 molar of E. And in this case, there's plenty of E to do that, so that means that D is the limiting reactant. So 4.5 molar of D will react with 1.5 molar of E. E and F are in a 1:2 ratio, so if 1.5 molar of E reacts away, you're going to form twice the number of molarity of F, which will be 3.0. Adding the columns, you'll have no D left over, 0.5 molar of E left over, and 3.0 molar of F are formed. Question number 3, write the correct equilibrium constant expressions for the following reactions. Equilibrium constant expressions are the concentrations of the products, each raised to their coefficient as a power, divided by the concentrations of the reactants, each raised to their coefficient as a power. In A, it should be the concentration of NO2 to the 4th, multiplied by, not added, the concentration of H2O to the 6th, divided by the concentration of NH3 to the 4th, multiplied by the concentration of O2 to the 7th. For B, products over reactants, it should be the concentration of NH3 squared multiplied by the concentration of H2O to the 4th, divided by the concentration of NO2 squared multiplied by the concentration of H2 to the 7th. For C, we now have a solid in our reaction, and as you recall, solids and liquids have constant concentrations. They're not variables, so you leave them out of equilibrium constant expressions. So in this case, it would only be the concentration of NH3 multiplied by the concentration of HCl. Solids and liquids, because they are not variables, do not appear in equilibrium constant expressions. In D, we have two solids, So the zinc sulfide on the reactant side and the zinc oxide on the product side are left out of the expression. And so therefore the equilibrium constant expression will be the concentration of SO2 squared divided by the concentration of O2 cubed. For E, we have a concentration of HCl squared multiplied by the concentration of O2 to the 1/2. So this is the first fractional coefficient we've seen, and the rules are just the same. Whatever the coefficient is, that becomes the exponent in the equilibrium constant expression, divided by the concentration of Cl2 multiplied by the concentration of H2O. Number 4, in a 2.50 liter flask at 298 Kelvin, 0.125 moles of SO2, 0.145 moles of O2, and 0.465 moles of SO3 are in equilibrium. Calculate the equilibrium constant for the reaction. Equilibrium constants are the ratios of product concentrations to reactant concentrations. So it's not the ratio of moles, it's the ratio of molarities. So we have to calculate the molarities of each of the 3 different substances that are in equilibrium. So the equilibrium concentration of the SO2 is going to be the moles of SO2 divided by the volume of the container, and that turns out to be 0.0500 molar. For the oxygen, it's 0.145 moles divided by the volume of the container. That turns out to be 0.0580 molar. Notice each of these, I'm dividing a pair of 3 significant figure numbers, so my answer is coming out 3 significant figures, and that's because beginning zeros are not significant figures. So the significant figure counting begins with the 5 in each of those. That's why they're each 3 significant figures. For the SO3, 0.465 moles divided by the volume of the container, 3 significant figure answer comes out to be 0.186, and you stop the number there. The equilibrium constant expression for this reaction is products over reactants. That would be the concentration of SO3 squared divided by the concentration of SO2 squared multiplied by the concentration of O2. And now that we know the 3 equilibrium concentrations, we just plug them in, we square the appropriate ones, and we'll get a numerical value which will be rounded to 3 significant figures. For the units, in the numerator I have molarity squared, but the denominator I have molarity cubed. So molarity squared divided by molarity cubed gives us units of molarity to the -1. So our final answer comes out 239 molar to the -1. Problem number 5. The equilibrium constant at 450 Kelvin is 1.25 times 10 to the second for the reaction given. NO gas plus 1/2 O2 gas is in equilibrium with NO2 gas. A, at 450 Kelvin, does the reaction at equilibrium favor products or reactants? That's determined by the numerical value of the equilibrium constant. If an equilibrium constant is greater than 1, that means when you reach equilibrium, you're going to have more products. If the equilibrium constant is less than 1, you're going to have more reactants in the container. It'll never be negative, so the value is always going to be positive. It's either a positive number greater than 1 or a positive number less than 1. And the equilibrium constant here is 125. That's definitely bigger than 1. That means that when you reach equilibrium, the container will contain mostly products. And so therefore we say the products are favored because you have more of them in the container at equilibrium. B, what is the numerical value of the equilibrium constant for the reaction 2NO plus O2 is in equilibrium with 2NO2? This is a related reaction to the first one given in the problem, except all the coefficients have been multiplied by 2. So if you multiply the coefficients by 2, that means you take the equilibrium constant of the original reaction and you raise it to 2 as a power. So multiplying the coefficients by 2 means the KEQ of the original reaction must be raised to the second power. If you raise 1.25 times 10 to the second power, you get 1.56 times 10 to the fourth, and that will be the equilibrium constant for the reaction the way it's written in part B. In part C, at 450 Kelvin, what is the numerical value of the equilibrium constant for the reaction 2NO gas is in equilibrium with 2NO gas plus O2 gas? This one, although it's related to the original reaction given in problem 5, it's more closely related to the one in B, and I find this easier to do. If you look at the reaction in B and compare it to the reaction in C, they're just the reciprocal of each other. They're the reverse. So if you ever reverse a reaction, you take the reciprocal of the equilibrium constant. So if we reverse the reaction in B, that will give us the reaction in C. So the equilibrium constant for the reaction in B must have the reciprocal of it taken. So if we take the reciprocal of the 1.56 times 10 to the fourth, and I'm going to use the guard digits that I would have calculated in part B, and I take the reciprocal of that, which mathematically is raising it to the -1 power, I'll get the equilibrium constant for the reaction in part C, which would be 6.40 times 10 to the -5th. Number 6, the equilibrium constant for the reaction N2 gas plus O2 gas is in equilibrium with 2NO gas at 2,130 degrees Celsius is 2.0 times 10 to the first, which is just 20 written as two significant figures. For the following conditions, determine whether the reaction is spontaneous forward or reverse, or whether it's at equilibrium. So in part A in number 6, they tell you in a 1.0 liter box, there's 0.02 moles of N2, 0.01 moles of O2, and 0.02 moles of NO. What we need to do is we need to calculate the reaction quotient for this particular box. And the reaction quotient is just products over reactants, but it's the molarities of each of the substances, not the number of moles. So I'm going to take the number of moles of nitrogen, moles of oxygen, moles of NO. I'm going to divide them all by the volume of 1.0 liters. Because I'm dividing by 1, it doesn't change the numerical value, but I want you to just realize that I'm actually determining the molarities of those. So the Q expression will be the molarity of NO squared divided by the molarity of N2 times the molarity of O2. And if I take the moles given for each of the 3 different substances and divide them by 1, I'm going to get the molarities, which are 0.02 molar for the NO, 0.02 molar for the N2, and 0.01 molar for the O2. If you calculate this out, this will give you the reaction quotient for this particular container, which is 2. And because it does not equal the equilibrium constant, that means that this particular system is not at equilibrium. All systems go to equilibrium, so that means the Q value will eventually become the equilibrium constant. So the 2 will eventually equal the numerical value of 20. So what does that mean it has to do? It has to get bigger. So if it has to get bigger, you've got to make a larger numerator, and the numerator is where the products are. So that means the forward reaction must be spontaneous. That's the only way you can make the numerator bigger so that the reaction quotient can increase from 2 to eventually reach the equilibrium constant of 20. In B, they gave you 0.2 moles of nitrogen, 0.01 moles of oxygen, and 0.02 moles of nitrogen monoxide. Dividing each of those by 1.0 liter will give us their 3 molarities. The molarities come out 0.02 molar for the NO, 0.2 molar for the N2, 0.01 molar for the O2. Calculating the reaction quotient for this particular system, it comes out to be 0.2. 0.2, because it doesn't equal 20, means the reaction is not at equilibrium. Our Q value here is lower than the equilibrium constant. It's going to eventually become the equilibrium constant, so it has to get bigger. The only way for a fraction to get bigger is if the numerator gets bigger, and that's where the products are, so you have to form more products. So just like in part A, in this case, we would predict the forward reaction would have to be spontaneous for the reaction to go to equilibrium. In C, they give you 0.2 moles of N2, 0.01 moles of O2, 0.2 moles of NO. Dividing them all by 1 liter, we get the molarity of all 3, and plugging them into the reaction quotient expression again, we'll wind up calculating the reaction quotient for system C, and that comes out 20. And because this equals the equilibrium constant, that means that this system is not going to have the forward or reverse reaction be spontaneous. It's already at equilibrium. Number 7, the general description of the equilibrium condition for a chemical reaction, which is the ratio of the equilibrium concentrations of the products to the equilibrium concentration of the reactants, is known as what law? We didn't cover this in class, but this was in the reading in the textbook, and that phenomenon is known as the law of mass action.